Okay, I want to review very briefly what we did last time because it's an important concept in terms of how we handle these uniformly distributed loads. They're quite common. And what we did was, for this particular shear diagram, what we do, we followed the arrows up to 22.5, but then we figured out what was the total load there. Well, the total load there is 3 times 15 is 45. And so we are working from left to right. I'm at 22.5 at this stage. And as I go all the way across here, what do I find? Well, the total there is my 3 times 15, 45. So I go down. The arrows are pointing downward. So that tells me to go down 45. So again, I'm at 22.5. I go down 45 at the very right end. Then I'm at negative 22.5. How do I get there? It's a straight line. The slope is what? Negative 3. It's pointing downward. It's 3 kips per foot, pointing downward. So my slope is negative 3. Then what do? I need to get the area of that triangle. I get the area of that triangle, and 1/2 the base times the height. I'm not going to go through that again. 84.375. So on my moment diagram, I start at 0, and then again I'm working left to right, and at this location here, I have an area of 84.375. So, and then again working left to right. This area is negative 84.375, and so it takes me back to 0. How do I get there is the other part of it, and then I notice this is a value of 22.5. That means that this has a slope of 22.5, so I draw on a very steep slope. This has a value of 0. That means the slope here is 0, so I draw a slope of 0. And there's only one way to get there. It's like that. Do not draw like that. It's not like that. Because those don't fit the slopes that we just got. So, and then this is 0, and this value is negative 22.5, so again, it's like that. It's not like that. Okay. So again, the basic, I've got, that looks like a bow tie in a way, and this is an upside down parabola, approximately. You need to know this shape. All right, so I want you to do this problem. I've gotten you started by giving you the reactions, and then I began the shear diagram. So what do? I start at 0, I go up 5. This total load is 0.4 times 10, which is 4. So I'm at this point here at 5 kips. I need to go down 4 because the total load is 4. That takes me to 1. How do I get there? It's a straight line. The slope is negative 0.4 because that is a 0.4 kips per foot pointing downward. Okay, so pause the video and do the rest of this. Do the moment diagram also. All right, I assume that you've done it. So again, we go up 5, down 4, and then there's nothing here, so I go straight across. Go down 8. There's nothing here, so I go straight across. I go up 7, takes me back to 0. So now what do I need to do? I need to find the area of that trapezoid. Well, you can all get the area of a trapezoid. It's 1/2 the sum of the 2 legs times the width. So 1/2 the sum of the 2 legs, 1/2 5 plus 1, times the width of 10 gives me 30 for the trapezoid. You can get the rectangles. So I start at 0, and the area is 30, so now when I get over to here, I'm at 30. How do I get there? Well, here the slope is 5. Why? Because the value of shear is 5. Here the slope is positive 1, which is less steep, because the value is 1, and the only way to connect it is like that. Don't connect it like that. That is wrong. Okay, so and then the rest, I go up area 2, I go down area 3, takes me back to 0. The slope is 1 because the value there is 1. The slope is negative 7 because the value there is negative 7. Again, to show the slopes, there's a slope of positive 5, there's a slope of positive 1. The only way to connect those is like that. Do not draw it like that. Now, I want to know what, an easy one here, I want to know the equation of that line we're going to find. That's going to be helpful. So how do I get the equation of that line? Well, I'm going to use y equals mx plus b, and since my y-axis is v, I'm going to have v is equal to mx plus b. Well, the slope m is negative 0.4, so there's my negative 0.4 times x, and then my intercept is 5. So v, in that range, v is equal to negative 0.4x plus 5. All right, so you do this one. Pause. I've done that much. Pause the video and solve this one. All right, assuming you've done that, so what do? I go up 6.43. This total load here is 5 times 2 kips per foot, which is 10. So I'm at 6.43. I go down 10. It takes me to negative 3.57. How do I get there? It's a straight line with a slope of negative 2. It's negative 2 because the distributed load is 2 kips per foot. So got that. Then what? Then I go over, up. That's the easy part. So I have to get my areas again. I got to get area 1, area 2. Area 3 is easy, so I'm not going to go through that. To get those areas, I need again to use my y equals mx plus b. It's straightforward. The slope is negative 2. The intercept is 6.43. So that gives me y equals negative 2x plus 6.43. Which means, since v is my y-axis, v is equal to negative 2x plus 6.43. I want to find the x value when v equals 0, that point. So I put in v equals 0 into this expression here, and I solve for x, and I get that I get x is equal to 3.22. So if that's 3.22, then this is 5 minus 3.22, which is 1.78. Knowing those dimensions, I can now get my areas, 1/2 the base times the height for those two triangles. And so I start my moment diagram at 0, and my area 1 is 10.35. I get that. How do I get there? Well, it's got to look like that. Why? Because the slope is 6.43 there. It's 0 there. There's only one way to get it. And again, do not draw this like this. That's not correct because that doesn't fit the slopes. And now the same reverse. The slope is 0 there. The slope is negative 3.57 there, and it goes like that. Again, this is our basic shape that we're going to see over and over. We got a bow tie there. We got a inverted parabola there, and then area 3 is negative 7.14. I'm at 7.17. I go back down to almost 0. It's close enough. There's some round off error. If we carried all the digits, we would get it exactly, but it's close enough. Again, in other words, I have a slope of 6.43, a slope of 0. There's only one way to get there. Do not draw this one. Okay. You can work this one, so pause it. I've given you the reactions and everything like that. Assuming you paused it, what do? We go up 12.23 over This total load is 3 times 6. It's 18, so I go down. I go down 18 at the right end of this. And so that takes me to negative 5.77. How do I get there? It's a straight line. I know that because the load is uniform, and it has a slope of negative 3 because I have 3 kips per foot. And then you can finish out the rest of it. I need to get the equation of this line because I need to get this x value there. So now it's a little bit trickier. I go that y is equal to mx plus b, which is v is equal to mx plus b. I know that the slope is negative 3, so I get negative 3x plus b. And now the b is not easy because it doesn't touch the intercept. But you know, if I extended this line, what am I looking for? I'm trying to find this point up in here. Now notice, if we've done this right, that value of that point is going to be bigger than 12.23 because it's up there. So that's a little bit of a check when you do this work. So, but what do? How do I get that value? I observe by looking at what we have for the shear diagram. I observe that at x equals 2, v is equal to 12.23. X equals 2, v equals 12.23. And so I could use this point, which is at x equals 8, v is equal to negative 5.77. I could use either one of those points. But I have to choose a point on this line. Do not choose this point. Do not choose this point, or this point, or this point, or this point, or this point. None of those points are on that straight line. So you have to choose points that are on that straight line. So I take my x equals 2. I put it in there. I take my v equals 12.23, I put it into there. And then I solve for b. You can all do this. This is basic trigonometry. I get b equals 18.23. And so there's the equation of my line. What do I want? I want to know where, the v is equal to 0. So I put in v equals 0, and I solve for x. So v equals 0, solve for x. I get x is equal to 6.07. Once I get 6.07, I know that that's 4.07, and that's 1.93. So I can now get all my areas. You can look at that, pause the video and look at the areas. And, I go up area 1. I go up area 2, takes me to 49.35. The other areas are negative, so I keep going down. And again, we have you can reason it out, we have our sort of bow tie shape there. And that means we're going to have this inverted parabola that looks like that. Now, I know you can all do this, but so I should say all. What I found is about 75% of you remember how to get a straight line, the equation of a straight line from the coordinates of 2 points. I'm going to review this one more time because some people struggle with this, but I'm going to do it very quickly. Another way to do this is I have point H and I have point J, and I can write the equations or the coordinates of my point H are 2, 12.23. The coordinates of point J are 8, negative 0.57, negative 5.77. So using your trigonometry equations from high school, the first point can be x1, y1. The second point can be x2, y2. And then what do we know? M is delta y over delta x, which is y2 minus y1 over x2 minus x1. I can plug that in. I get m equals negative 3. I'm using y equals mx plus b. And at this stage, I need to get b. Well, what do? I use either x1, y1 or x2, y2. I plug those, I choose one. I'm choosing x1, y1, which means that I put y1 in for y, I put in x1 in for x, and so I put in my 12.23. I put in my 2, so I'm using, don't mix x and y. I put those in there, I solve for b, I get that, and now I have the full equation. Okay, so you need to be able to do this. You can all do it. Spend just a little bit of time with it. All right, next one. I'll do another example here. I've given you the reactions. So I go up 0.8 over. This total load is 2 times 4. 8, arrows are pointing downward, so I go down 8 to negative 7.2, up 11.2 over down 4. There's my shear diagram. Again, to be able to get the areas, I've got to get the equation of that line. And I'm going to use y equals mx plus b, or v equals mx plus b. And I know the slope is negative 2, so I get v is equal to negative 2x plus b. I'm going to use this point. Again, do not use this point, or this point, or this point, or this point. You could use this point because it's on the line. So I'm going to use this point here, which is x equals 1, v equals 0.8. So I have x equals 1, v equals 0.8. I plug this in. There's v equals 0.8. There's x equals 1. I solve for b, and I get b is equal to 2.8, giving me the equation. That line is negative 2x plus 2.8. And I now want to know, I need to know this point here. So at v, I want to know v equals 0. I solve for x. So I have the equation of my line. I put in 0 right there. And I solve for x. I get x equals 1.4. So you need to know how to do this. So I get my areas. I get all my areas. In other words, if let's make it clear. This total distance is 1.4. That means, because we always take x equals 0 at the far left end. I know there are other ways you can do this and put in a different x value. I don't want you to move the x values around for a reason we'll see later on. We all have to be on the same page. I want x equals 0 at the far left end. And that means that this is 0.4 and that's 3.6. We can now get all of our areas. And I now go up area 1, I go up a little bit area 2, down area 3, up area 4. And there's my moment diagram. Now, for this problem, notice I have the distributed load going upward. Well, what's the impact of that? Again, I have we're going to start here. We have the reactions. And I start at 0, and that total load is 6 times 4 is 24. So I'm going to go up 24 like that. I know the slope is positive 6. Why is it positive 6? The arrows are going upward. Since the arrows are going upward, I get an upward slope of 6. So it's positive 6. And then straight across, down, over, up. You can all do that. The areas are easy to get now. But now when we do the moment, so the areas are easy to get, you can get all those. When I do the moment diagram, what? The value of v is 0, so my slope is 0. Here the value of v is 24, so my slope is 24. How do I get there? It goes like that. It's not like that this time, okay? So pay attention to these, and then you can get the rest of these. I'm not going to go through it, but notice I have a slope there, a slope there. The only way to get from there to there is like that. It's not like that. So do not do that. What I want to say here is the sign convention. We've been talking about, I used the sign convention, I didn't talk about it, so I just want to point it out now. Now notice when we did our free body diagrams at the beginning of this discussion of all of this, I didn't say anything, but I always had V going down, N going to the right, M counterclockwise. I did that because everyone uses this sign convention. So you're going to be using this for the rest of your life. It's everybody uses it, not just me. Everybody uses this same sign convention. And it has some implications for us a little bit later on that we'll point out. Now notice, I always also took the free body diagram of the left side of the beam. I could have taken the left side, or I could have taken the right side of the beam and drawn the free body diagram. Now, if you do the right side of the beam, you have to be consistent with our sign convention. In other words, if I'm looking at, these are adjacent free body diagrams. They're right next to each other. They're touching. So if I draw V going down there, I have to draw V going up there. If I draw N going to the right there, it's got to go to the left over there. If I have counterclockwise being positive there, I have to have clockwise being positive here. So that is our sign convention, and these are positive, and we will stick with that. Okay, I'll stop there.